Okay, so let me start. So as you might be able to tell from the outline that I posted online, I'm running slightly behind in what I've planned to do. And so what I decided to do, therefore, is today I'm going to mix Blackboard and slides, because slides is going to help me to go through a couple of things more quickly. And I'm assuming that the first part of this lecture you kind of are familiar with anyway, and I just want to highlight a couple of just the basic principles of effective field theory that we're going to use when we apply it to inflation. Then when I discuss the actual UV sensitivity of inflation, I want to do it on the board just so that we can discuss the basic aspects of it a bit more informally. And then the next lecture, in fact, I had always planned to do in slides, because I want to survey kind of the different types of ideas that have been out there about realizing inflation in string theory. And doing that on the board just wouldn't get me very far. Okay, so the next lecture will be with slides. This one will be split. Of course, the disadvantage of using slides is that, first of all, I actually hate doing it, and it has a danger that I go too fast. Okay, so please just slow me down by asking me questions and things like that. I can go to the board if anything needs to be elaborated on and so on. Okay, so usually I think it's nicer to do it on the board, but I want to catch up a little bit on some of the topics. Okay, so the outline of the lecture today is going to be the following. I'm just going to review very basic facts of effective field theory. Of course, implicitly and explicitly, this has been used in all of the lectures so far. And I just want to make sure that we're on the same page, we all agree on the basic rules, and I want to formulate it in such a way that it would make it very easy for me to apply it to inflation. In fact, the application to inflation will be very fast after we talk through some of these basic principles. So that's what I'm going to do after that. I'm going to show you how effective field theory is applied to inflation. And we're going to discover that, in fact, the effective field theory that describes inflation is of a kind of a peculiar type that we're not very used to in particle physics, in the sense that it's UV sensitive, that it depends on our ignorance about physics happening all the way up to the Planck scale. Okay? That's usually not the case. You can run the LHC and not have great uncertainty about what you will be finding, even though you don't have a complete theory of quantum gravity. We do have a great uncertainty about the basic dynamics of inflation because we don't have a complete theory of quantum gravity. And so that's it's very rare, in fact, that we have this sensitivity to Planck scale physics in any physical systems. The only one or two other examples I know, like proton decay and things like that. But it's a kind of a unique status of inflation that it is sensitive to processes happening all the way up to the Planck scale. And so there are two attitudes you can take towards this. Either you can think that's a problem, or you think it's an opportunity because it provides a window into these unknown processes in principle. Okay? But we will see what this means when we get there. Okay, so I want to start off, and I can do this as fast or slow as you like, depending on how you speed up or slow me down. So I just want to go through very the basic idea behind effective field theory. And of course, effective field theory starts with the trivial sounding realization that nature comes with many scales. And in particular, the physical systems that we understand best. In those physical systems, there are hierarchies of scales, so those scales aren't sitting on top of each other. And because there's hierarchies of scales, we can do some systematic expansion of low energies over high energy behavior. So this means if we can coarse grain over the short distance behavior and get an effective theory for the long wavelengths or light, low energy dynamics. Okay, so we often do this implicitly anyway in physics when we just decide to speak about physics at a certain energy scale without taking into account short wavelength processes. And effective field theory just gives us a general framework for systematically incorporating our ignorance about the short scale physics and estimating the error that we're making by ignoring some of the high energy processes. And this is even useful when we don't know the microscopic theory, or it's particularly useful when we don't know the microscopic theory because it allows us to be conservative and parameterize our ignorance in the most general way. Okay? And so of course, the history of particle physics has developed in this way from the bottom up. So at early times, we were studying things at energies of order the mass of the proton. The interactions between neutrons and protons can be described by 4 Fermi theory at those energies. But the coupling strength, of course, is an inverse mass scale. So that means that scattering amplitudes in that theory will diverge with energy. And there's a critical energy at which these type of amplitudes that you calculate start to violate perturbative unitarity, and there's a breakdown of this effective description. So the theory is smart. It tells you that it only has a limited range of validity, and this limited range of validity for Fermi theory is all the way up to, or just up to like about 100 GeV. And of course, these days we know what happens at 100 GeV. We start to resolve this contact interaction into an exchange diagram of the Standard Model. The new particles, the W bosons, that regulate this perturbative unitarity. But then even the Standard Model itself we don't think is a complete theory, especially when we combine it with gravity, where you have a similar non-renormalizable coupling, Newton's constant, amplitude scaling exactly the same way as for the Fermi theory. And this also breaks down, of course, now famously at the Planck scale. Again, we think that new physics comes in before that happens, and so my lectures is going to assume that this new physics is going to be string theory. So below you hit energies afforded the Planck scale, you start resolving the short scale structure of this more complete theory. Okay? And so the inflation most commonly is imagined to lie somewhere in between here, the processes that are described by the Standard Model and the UV completion of the Standard Model together with gravity. Since we haven't been very successful of trying to embed inflation into the Standard Model itself. Okay? This might change if we have better ideas of how to do this, but at the moment it looks like we need some kind of beyond the Standard Model physics. And in the next lecture I'm going to in fact describe how you might get that beyond the Standard Model physics from a more UV type of attitude. Okay? But let me go back and actually let's start by studying toy models of complete theories. So the toy model that I want to consider is a set of light fields, and I'm going to collectively call all of the light fields little phi with masses little m. And then the heavy fields associated with the UV completion of that theory with with a larger mass capital M. There's a cutoff scale that divides the regime of applicability of this effective theory, which has to be lower than the mass of these heavy states that I'm trying to integrate out. And so if the full theory is known and if it's computable, so if it's a weakly coupled theory, for example, then we can in principle integrate out these heavy fields explicitly, which means that we can do the path integral in two steps. We can first do an integral over all of the heavy modes and the high frequency, and strictly speaking also I should be integrating over the high frequency components of the light fields. So that I get, after this first integration, I get an effective action just for the light fields, and then I can do a second part integration over the light fields to compute correlation functions and things like that. Okay? In practice, we rarely do this. If the theory is really weakly coupled, we can do a matching calculation. We just have to impose that scattering processes with external light particles have to agree in the effective theory and in the full theory. Okay? So let me illustrate this with this simple toy model where I have two massive scalars. Here for the light scalar, I'm also allowing for a quartic coupling. And then these two scalars are coupled to each other by this marginal interaction. And there's a coupling strength G, which defines how strongly these two fields are coupled to each other in the UV. Okay? So matching then means that I can compute scattering both in the effective theory and the full theory with just external legs, because I'm doing things at low energies where I'm not able to produce on-shell heavy particles. And so these amplitudes have to agree. So what I'm doing is I'm adjusting the coupling strength of the effective theory such that order by order in perturbation theory it agrees with the full answer. Okay? So for example, if I look at some 2-to-2 scattering process, in the effective theory that's described by some contact interaction, just like in 4 Fermi theory. In the full theory, there's a loop expansion that describes a tree-level process, a one-loop process, and then higher loops. So here in the full theory, I can do an expansion in the UV coupling. So at every order in the loop expansion, I'm adjusting the effective theory parameter to match this answer. Okay? So this is how we can construct, just at a diagrammatic level, we can construct the entire effective theory just by matching to all possible processes in the full theory that only have light states as external states and possible heavy states as virtual particles in loops. Okay? Okay, so then let me highlight that there are two effects that these heavy fields can have. So first of all, they can renormalize the IR couplings of the effective theory. So they renormalize the mass, for example, by renormalizing, this is a one-loop renormalization of the propagator, and they can renormalize the quartic coupling in the following way. And so for this toy model, you can calculate what this one-loop correction is to these quantities. So the mass is renormalized like this, for example, and the quartic coupling like that. I should highlight, so here I've chosen a particular regularization scheme. Yeah? I've chosen a hard cutoff in momentum space because I've split modes into high momentum and low momentum modes. But this contribution to the renormalization is scheme dependent. So in a different regularization scheme like dim reg or things like that, this power law divergence wouldn't be there. So I shouldn't never overinterpret such power law divergences because they're unphysical. Okay? Nevertheless, there's a corresponding piece that actually depends on the physical mass of the heavy state that comes with associated with the same UV coupling. And that's why often people heuristically associate the renormalization with the cutoff scale of the theory because they're similar. But you could cook out examples where they're quite different, so you have to be a little bit careful of overinterpreting the power law divergences. Okay, so I won't do this. I would just ignore this unphysical contribution. And if I were to do a dim reg, I wouldn't even see it. I would only see these logs. But nevertheless, there's a large contribution in principle to this mass, unless somehow this UV coupling is very small. Okay. So if this UV coupling is of generic strength of order, if this is an order 1 coupling, then I would be renormalizing this mass by a large amount. And it would be a puzzle why I have this light field in the effective theory in the first place. Okay? So having light scalars in effective theories, in fact, without symmetries, often looks unnatural for this reason. Okay? And of course, the hierarchy problem for the Higgs is just a manifestation of that. And for the inflaton field, we will have a similar problem that we also want to have a scalar that's light relative to all of the high energy scales that we have ignored. And it's a puzzle how we keep this light in the presence of couplings to these UV degrees of freedoms. Okay, that's one effect. Second effect is that it can create new interactions, new non-renormalizable interactions, in fact, an infinite series of them. And so here I've just shown you one diagram that's consistent with this UV theory that induces a 5 to the 6th interaction suppressed by the mass scale of the heavy physics. Okay? But you note that these terms, they are irrelevant at low energies in principle, and they decouple if I choose the scale of the physics to be heavy physics to be very high. Okay? So as they should. So if I choose this scale m to be close to the Planck scale, then usually these make tiny contributions to the low energy Lagrangian. Especially for standard model processes, these will be completely irrelevant. But as we're going to see, for inflation processes like this, in fact, will make order 1 contributions to our dynamics. Okay? Okay, so this was then just to illustrate that everything that's consistent with the symmetries of the full theory will be is allowed, and not more than that. In fact, it's compulsory. Yeah? So at some order in this loop expansion, you will generate all possible contributions in this effective Lagrangian consistent with the symmetries. So the toy model that I had previously, in fact, had a Z2 symmetry. I was only writing even terms in phi. So there was a phi to minus phi symmetry, so I only should be generating terms that are even in phi. And in fact, you do. And you will not be able to write a loop that has an odd power of phi as external x. It's just inconsistent with the symmetries of the Lagrangian. And so it's inconsistent also with the Feynman rules of that theory. Okay? So in principle, of course, and then famously, you have an infinite number of terms, but they can be organized in a power series of energy over mass. So in order to describe observables, you only need a finite number of these operators. Okay? So that's from the top down. It gives you kind of a sense for what can happen, and if the theory is perturbative, how the IR couplings depend on the UV coupling. This is not something I highlighted, actually, but here you can see, for example, here I have 3 powers of the UV coupling. For the mass, I had 1 power of the UV coupling. Here I have 2 powers of the UV coupling. So for weakly coupled completions, the IR parameters will be determined in terms of the strength of the coupling to the UV. Okay? And so this toy model kind of illustrates that. Okay, but often it's the case that you actually don't know what or most of the time in our business, at least, it's the case that we don't know what the full theory is. And then we still use effective theories to write down an effective Lagrangian from the start, from the bottom up. So what we do is we identify the relevant degrees of freedom that we choose to describe at a given energy scale. So for the standard model, it would be all the particles of the standard model. You identify the symmetries that are relevant to those particles at that energy scale. So the gauge symmetries, for example, of the standard model. And then you write the lowest dimension operator that's compatible with these symmetries. And depending on the accuracy that you're trying to describe the experiment by, you include higher orders in that expansion or not. Okay? Okay, and so I hope this was very basic, but I also hope it hasn't bored you too much. So, any questions about this? No? Good. Okay. So then now it's going to be very easy for me to apply the same logic and procedure to inflation. So here first we have to identify degrees of freedom that are relevant for inflation. And so at a minimal level what you have to have is you have two massless or very light fields, which are the inflaton field and the graviton. What we have studied so far was a toy model that just minimally coupled a canonically normalized inflaton field with a potential to the graviton like this. But now this effective field theory philosophy obliges us to consider what happens when we allow for corrections added to this Lagrangian. And so we want to study what happens when I allow the most general set of operators consistent with some kind of symmetries that I'm assuming for this theory. Okay? And we want to identify how strong of an assumption do I have to make about these terms in order to preserve the success that I've kind of achieved by just studying this toy theory that was just, pretended to be ignorant about physics at very high scales. So the first question we might ask is, what's the cutoff lambda for this effective theory? And of course, we don't know for sure, but we don't know what particles live at very high energies. But we have bounds. So since we're describing a theory coupled to gravity, and we know that graviton scattering violates unitarity at the Planck scale, it's hard to imagine that you can choose the cutoff scale to be larger than the Planck scale. And so typically, we won't allow us to do this. Or at least we will consider it a very strong assumption if you're forced to make that leap of saying that the only heavy physics that we couple to is something that's higher than the Planck scale. But we're going to see that this is one of the conclusions that we will be reaching, that you naively run into trouble if the cutoff isn't of order the Planck scale or larger. And then in any weakly coupled completion of gravity and quantum mechanics, you typically have weak coupling scales that suppress the cutoff scale or the scale of new physics. So in string theory, the string scale for weakly coupled completions typically is smaller than the Planck scale, and so we even have an expectation that the cutoff scale should be smaller than that. Second question then is, what are these Wilson coefficients Ci for each of the operators? Of course, for single operators, there's you can always rescale Ci and adjust your cutoff scale lambda. What I mean here is that once you're fixed kind of the cutoff scale for one operator, what's the relative size of the Wilson coefficient for other operators? And so the problem here is, of course, that we know very little about these couplings to Planck scale degrees of freedom, especially if we're not studying it explicitly in string theory. And one of the motivations is going to be that we want to study it explicitly in string theory because we're going to be sensitive to what we are assuming about these couplings. Okay? So my attitude here is that without a good reason, if we don't have a good reason, then typical Wilsonian naturalness tells us we should be assuming order 1 couplings of all the fields not protected by symmetry at the cutoff scale. And that then, as we saw, will translate roughly in order 1 Wilson coefficients in the low energy limit. But sometimes you do have a good reason, and you do have a symmetry that protects you from couplings to massive fields. And that then also suppresses the possible irrelevant operators that it can generate. Sorry?
Maybe that goes a bit too far afield.
Yeah, we can. Let's talk about it later. It's a bit of, yeah. But it's basically what I said here. Okay. But in the absence of symmetries, you write down everything consistent with those symmetries with order 1 coefficients. Okay. And so these Wilson coefficients are order 1 if you choose Wilsonian naturalness as your principle of. Okay, so as I advocated that sometimes there's a good reason for suppressing couplings in the IR or in the UV. And most of the time, those good reasons are global internal symmetries. Like if you have a spontaneously broken symmetry, like this famous one here, you generate a shift symmetry for the angular direction here in this Mexican hat. And so that can suppress all polynomial couplings of the inflaton or any other scalar to massive states. The problem is that here we're trying to formulate this theory in quantum gravity, and so there's a law that quantum gravity doesn't like, continuous global symmetries. There's certain thought experiments that you can do about the evaporation of black holes that violates those continuous global charges. And so, okay, then you can argue about these processes are non-perturbative, so maybe they come with non-perturbatively suppressed coefficients, or maybe you gauge the symmetry and it becomes an accidental global symmetry in the IR. This is all fine, and these arguments are not supposed to be airtight kind of arguments. That's why they're called folklore. But nevertheless, it means you're assuming some kind of structure, and it would be nice to establish that kind of structure that you're assuming in a theory where you have actual information about couplings to UV degrees of freedom, okay? And that's what people use as their motivation for studying inflation in string theory. So that you can actually, you can show that the words that people are using to relieve their conscience and sleep at night about these things, that they actually can happen, okay? And so we were going to see examples in string theory often where it's very hard, in fact, to make these things happen. Okay, so let me describe, and so this part I want to do on the board so that we can discuss it a little bit. So let me describe what all of this implies for inflation. So how does this UV sensitivity of inflation manifest itself? So there are two classic examples of sensitivity to UV dynamics of inflation. The first one is universal. It basically holds in any type of inflationary model that you write down, and the second one is more specific. Okay? So let me describe the universal one, which I'm sure you have heard about. The so-called eta problem. So we have seen in the first few lectures that in order for inflation to last, this eta parameter, which is m Planck squared v double prime over v, has to be less than 1. And in fact, something I didn't quite show explicitly, but actually in my notes I set it as an exercise for you to show, is that this eta parameter also appears in the slow roll prediction for the ns-1 scale invariant predictions. So in fact, you don't just have to have this less than 1, but you typically have to have this about equal to 0.01, okay? The size of the ns-1 deviation from scale invariance. Also in many models, in fact, the inverse of eta it tells you the total number of e-folds of inflation to the CMB scales, which we know to be 60. So this eta parameter is often 1 over the minimal number of e-foldings that we need. But then you see you can write this more physically as the mass of the inflaton field at some point in field space divided by 3 times the Hubble parameter squared. Okay? So the potential sets the size of the Hubble parameter, and V double prime sets the size of the mass. So what we're requiring is the small hierarchy between the mass of the field and the Hubble scale. Okay? But this hierarchy is sensitive to UV physics. For the reasons we saw before, okay? Okay? So first of all, if there's no protective symmetry acting on this field, it receives radiative corrections. Okay? Okay, so it's the same as before. The radiative correction to the mass of the scalar is of order the UV coupling times the mass of the heavy field. But this mass of the heavy field has to be chosen to be larger than the Hubble scale. Okay? Otherwise it's quantum mechanically active during inflation, and I have to reevaluate how I computed my spectrum of fluctuations in the first place. Okay? So any field, this Hubble scale is actually the scale of our experiment during inflation. That's when the modes are freezing out. And so we have to include all fields that are light relative to the scale in our effective theory that we're trying to describe at the energy scale of order Hubble. Okay? So since we think of this as heavy degrees of freedom that aren't included in our EFT, this has to be chosen higher than Hubble. Okay? And so this leads to a delta eta gm squared over Hubble squared, which is bigger than 1, unless I have a reason to believe that the inflaton field is very weakly coupled to anything at higher energy scales. Okay? So that's the effect that the UV physics can have, and it will have exactly the same physics on this scalar. And then the second effect that we can have is that you can have corrections from high dimension operators. So, for example, there can be a correction to the inflaton potential, which scales as the leading order part of the inflaton potential times phi squared divided by the cutoff scale squared, or m squared. And this leads to a correction in the eta parameter, which is of order m Planck squared over lambda squared, which again is greater than 1 unless this effective cutoff scale can be chosen to be bigger than the Planck scale. Okay? Which is kind of equivalent to that statement here. Yeah? A very weak coupling to massive fields will erase the effective cutoff scale in this way. So you require this inflaton field to be weaker than gravitationally coupled to everything living at the Planck scale. Okay? And so the nature of these problems are different. So here, I think this problem, you can appeal to a global symmetry because it's just a symmetry that has to hold at the level of relevant and marginal operators in this theory. But then, if you believe this law that quantum gravity doesn't like them, you're obliged to add symmetry breaking irrelevant symmetry breaking operators that become important at the cutoff scale. And what we're seeing here is that even if you can arrange this, you're still facing this second issue. Okay. Just as a side remark, what's often also used, of course, to stabilize scalar masses is supersymmetry. That doesn't help you with this one because, of course, supersymmetry necessarily is spontaneously broken during inflation. And so at the minimal level, this supersymmetry breaking will induce a mass splitting that is of order the Hubble scale. Okay? But you shouldn't confuse that it's a specific feature of supersymmetry. So sometimes you hear people getting confused about the supergravity eta problem, for example. Yeah? Which the name of this word makes people think that it's a specific problem that arises when you're trying to formulate inflation in supergravity. It's actually quite the opposite. Yeah? Without supersymmetry, you would have a much larger radiative correction to this. And supersymmetry gets you down to this level of mass splitting. And so whenever people then talk about, for example, that inflation is 1 part in 100 fine-tuned, okay, that the mass of the inflaton has to be fine-tuned by 1 part in 100, this is always when you already imagine that something like supersymmetry was stabilizing you at the Hubble scale and then tuning this number. Yeah, if you didn't have supersymmetry and you have large corrections from heavy physics, the tuning would be much, much more severe than that. Okay? So it's good to appreciate that these things that people mean implicitly but might not not always tell you. Okay. Does anybody have a good guess or a good explanation for why the mass splitting in supersymmetry is Hubble? So intuitively, if you think about supersymmetry, loop corrections from fermions and bosons at very high frequencies, okay, supersymmetry actually is restored because you don't see the expansion of the universe. So deep inside of the horizon, the theory will still look supersymmetric, and there will be an exact cancellation between loop contributions to fermions and bosons. Okay? But then as you're reaching frequencies of order the horizon scale, curvature couplings kind of will modify your propagators for the fermions, and the boson won't look quite the same. And so you will get corrections to this cancellation between fermion and boson loops at the order of the curvature scale of the spacetime. And so that's why, this mismatch will be of order the Hubble scale for that reason. Okay. Okay, so this UV sensitivity is universal, and then there's one that's specific to models of large field inflation. So let me make this a statement and then prove it for you. So there's a famous statement, of course, that observable gravitational waves require that the inflaton field travels a distance which is at least the Planck scale over the entire observable range of inflation. Okay? So what I mean by this is that there's a certain moment in field space when modes cross the horizon, and specifically the modes that we observe in the CMB, and then there's 60 e-folds afterwards until inflation ends at some other point in field space. And so you can prove this inequality, that this distance in field space between the time when the CMB fluctuations were created or were crossing the horizon during inflation and the time when inflation ended has to be bigger than the Planck scale. Okay? So let me prove this to you. It's called the Leith bound. I just proved this to you because I can show you this is the quickest way to get famous. Okay? Because as you're going to see, I don't need more than this space to prove the bound, but it had significant psychological effect on people. It's just sometimes there are hanging fruits that are in front of you. Anyway, okay, I didn't say this. Okay, so first of all, so we get to this immediately just from what I told you last time. So recall last time we calculated the amplitude of scalar fluctuations. And so last time I wrote this in terms of epsilon, but we also had an expression that was relating epsilon to phi dot. So that same amplitude can be written as h over phi dot squared times h over 2 pi squared. Okay? So it had two factors, the zeta fluctuations and a conversion from canonically normalized fluctuations to curvature perturbations. And then tensor fluctuations had an 8 pi over m Planck squared that comes from the Einstein-Hilbert normalization. And then again, h over 2 pi squared. Okay? Then I also told you that the tensor to scalar ratio R is just the ratio of these two amplitudes. And so if I take these two expressions, that a ratio can be written as 8 over m Planck squared, 1 over h d phi dt, all squared. But h times dt is also dn, the differential change in the number of e-foldings during inflation. So let me just copy this. This is 8 over m Planck squared d phi dn squared. Okay? So you see immediately that the size of the tensor to scalar ratio is just determined by the speed of the field when measured in units of the e-foldings of expansion time. Okay? But then you can integrate, so you have the speed, you can integrate that speed to get the total excursion. So imagine you have a theory like this, where phi is here, and we have the inflaton potential here. So this field is rolling down. There's a critical field value that I'm going to call phi CMB, which corresponds to the moment when fluctuations in this field will cross the horizon and later become the CMB fluctuations. And then 60 volts later, the slow roll conditions are violated and inflation ends. So what we want to determine is we want to determine the total excursion delta phi from here to here. Okay? And it will be a lower bound in the total excursion during inflation full stop, because of course we typically believe that there's more inflation happening to the right of this plot. So now we just have to perform one integral. So it's delta phi over m Planck is an integral from 0 to 60. So I'm defining 0 as the end of inflation and 60 the moment when the CMB fluctuations were created. dn square root of r. And so in principle, r could be a function of n, because the speed of this field could be slightly varying as I'm rolling down the potential. However, at least in the slow roll expansion, this time evolution of r is second order in slow roll. So at leading order in slow roll, this is just a constant. And then at second order in slow roll, you would have a time dependence of r. You can take this into account, but let me just do the simplest case so that we can do it in just one more step. So if you assume that r doesn't vary throughout inflation, which effectively means the epsilon parameter is nearly constant, then you can pull this outside of the integral. You just get 60 from the total number of e-foldings. And then putting in numbers, you find that r divided by 0.01 to the power 1/2, okay, determines the total field excursion during inflation. Okay?
How much does this depend on the fact that it's a single field inflation?
Not very much. You can actually show. So actually, in our review, okay, we have all the possible ways people have tried. This looks so simple that you might think, let me just try to get around it, some different ways. So some people have tried to get around it by making this vary in time quickly, yeah, so that you have, large tenses happening somewhere here, and then somehow epsilon drops very small, but then you have to come back. And anyway, we cataloged all the things that people have tried to do, and I don't find any. And in fact, so multiple fields is, of course, one immediate possibility. Those actually typically just add scalar power, and they make the problem worse. So a lot of the things that your initial reaction might be to changing this actually make things worse. Okay? Yeah. The other possibility that I've studied a little bit was what if it's not a canonically normalized field, but you have strong kinetic interactions where things do change. And then it naively looks, if you have a naive interpretation of what you mean by delta phi, that you could actually evade this bound. But what you actually then discover is that you just shift the problem. Yeah? So once you have large kinetic interactions, you have to worry about corrections to your kinetic part of the Lagrangian rather than just corrections to the potential. Anyway, I'll tell you later. Okay. Okay. So where does the statement come from? So as I was saying yesterday already, we typically think of gravitational waves as being observable if r is greater than 0.01. And that's how we get this link between observable gravitational waves and delta phi greater than m Planck. Okay? But you should notice that this is a quite amazing coincidence, because this number here, this 0.01, is really determined by astrophysics. Yeah? So a priori, this could have been 10 to the minus 4, 10 to the minus 6, and so on. And the reason it's 0.01 is is dust and all this kind of stuff that we were talking about yesterday. That determines kind of what we can realistically, and in the future, this number might change a little bit. But this is the number that we can realistically see in the next kind of 10 to 20 years. And after that, it's going to be hard to dig out the signal from all the astrophysical confusion. So that's a number that's determined by astrophysics. But then, of course, that number here is kind of a fundamental constant of quantum gravity. Okay. So in some sense, we have been lucky that like nature has put us in a galaxy where the amount of dust that's spread out, with magnetic fields that have been sourced by turbulence and supernova explosions and so on, is just in the right way, so that it makes it a probe of quantum gravity if we get down to these values. Okay. Any questions about this life bound? Okay, so let me just, just really to drive home why we're shocked by this. So what we require in order to produce, significant tensors, we require a potential that looks something like this. In particular, something that's smooth over a distance that is large in Planck units. Okay. So we want the field to be evolving smoothly over distance in field space that is large in Planck units. But from everything I've told you about generic expectations in effective field theory coupled to Planck scale physics, we expect, and I definitely put expect into quotations because I get into trouble if I say anything stronger than that. So genericity and expectation and so on, of course, are vague concepts. I don't want to overemphasize what we do or do not expect generically. But nevertheless, in the absence of kind of symmetries, what I've showed you so far was that we can have corrections to the potential, an infinite series of them with kind of order 1 Wilson coefficients and phi over some cutoff scale I, okay? Say from 2 to infinity. So since we're scared to imagine having a cutoff scale larger than the Planck scale, we typically expect that this potential actually has structure on a distance scale in field space that is small relative to the distance scale that we require it to be smooth. Okay? But then if you have a large number of these terms, it would be an incredible conspiracy that all of these coefficients kind of align themselves in such a way that it looks like this. That consistency might be a symmetry, and then actually these terms aren't there. Yeah? But if you just were to randomly pick Wilson coefficients and have all of these operators together, what you would be generating is a shape like this, which will have structure of order the cutoff scale of that theory. Okay? So in something like this, you would not produce large gravitational waves because you would get stuck somewhere here or here, or this wouldn't look anything like our universe. Okay? And so notice also, but I've said this a couple of times now, that the UV sensitivity of inflation persists even if you push this cutoff all the way to the Planck scale. Okay? So it's not enough to suppress couplings to massive fields that are lighter than Planck. You really need to deal even with this Planck slop degree of freedom, living at the Planck scale. Okay? And so this, of course, is what we're trying to do when we try to study these couplings explicitly in a realization where we have access to couplings to Planck scale degrees of freedom. Okay? Yeah?
Do you think the amplitude of the fluctuations to also be of order lambda?
The amplitude of these fluctuations here, phi?
Yeah, just in your diagram. Because I'm wondering if the height of those fluctuations would also be of order lambda.
I think a priori yes, but it's related to the fact that we also have a tuning, maybe a tuning to explain the size of the density for the 10 to the minus. There's a built-in 10 to the minus 10 that we have to that we usually put in by choosing the scale of the potential. Yeah. Of course, I think what you're referring to is kind of like the cosmological constant problem, that you have a lambda phi to the fourth vacuum energy contribution to your potential, and so generically the height of that would, yeah, and so. Yeah, so this lambda phi to the fourth kind of would have to be matched in such a way that it produces the 10 to the minus 10 of the vacuum fluctuation, of the density fluctuations. So there's always also the cosmological constant problem that you can ask for inflation, which determines basically the height of this potential at the end, and that's a tuning that if I could explain, I would have solved the cosmological constant problem. Okay, and
no,
so.
I wasn't talking about the height or
Yeah.
the location of the potential on the vertical axis. I was talking about the size
Of these things?
fluctuations.
I don't think so, because you still, I mean, you can typically still suppress them by low energy. These are still an expansion of energy scale over lambda. Yeah. So there's still a small ratio well, okay. Everything has broken down once I go to large waves of this, so it's really hard to say any, yeah. I don't think we should be interpreting this potential when we have the field, excursion that has a super Planckian wave, because clearly this expansion is just nonsense. So it's not that you should really try to make this work in some sense. It just highlights that, and also I should highlight that this once I accept some kind of expansion like this, it's not solved by fine-tuning. So the eta problem I could solve by a single fine-tuning. I take two of the lowest dimension operators, this dimension 6, for example, and cancel it against another mass term. And so it's at one single tuning of a mass parameter, yeah, which, depending on your attitude, you might feel good or bad about. Okay. Here, there's no tuning that will help you, because you would have to tune an infinite number of these coefficients, yeah. So it really begs just for some deeper explanation. Yeah. So it's nice in that sense that it tells us that there has to be some actual nice physical mechanism. If this is really true, there has to be a reason for why it looks like this, and it's not a conspiracy of an infinite number of arbitrary terms in a non-symmetric theory and stuff like that. So these kind of theories with large tensors are different in a sense from theories with small tensors. So a theory that produces small tensors could look like this, and you could just accidentally be inflating on some hilltop like this, and a small range is enough to produce the successful inflation with large tensors. So there you could do things by fine-tuning, and you could be just living on a landscape with random terms in the potential, but not for large tensors. Okay. We can talk about it later if you want to know more. Okay. Any other questions? Okay. So if not, then I want to switch to my last part. And so as I said, most of this I want to do on the board, but again, if you don't ask me questions, I will go do this too fast. And so, yeah, please stop me and we can talk about individual aspects of this in more detail. So what I want to do, and this will occupy the rest of today, so 10 more minutes, and then all of next time, is I want to give you a survey of basically everything that was described in here. Okay. This is 400 pages, so clearly I'm not gonna tell you everything that's in there, but I'm gonna pick out a couple of things that I think are illustrative. And in fact, I think the basic principles, the basic lessons that we have learned over the last couple of years is actually a small number of them, and those small number of basic lessons I think I can tell you in an hour. And then here you find many examples of this that you may or may not care about. Okay. So the first thing I want to do is just to give you an overview, and so I basically want to show you how string inflation fits into this framework of EFT. So the added benefit that we have when we're formulating things in string theory is now that all these abstract scales that I was defining here, like the cutoff scale lambda and so on, they get physical meaning. Okay. So I want to show you the different energy scales that we have in this theory, and also the scalar field phi will have physical meaning in specific examples, so we can be more concrete about all these things that I try to wave my hands about genericity and things like that. Okay, so I'm going to do this first. This is probably going to do all I'm going to do today. And then we will have to grapple with some of the details of how this works in practice. Okay? And the devil really is in the details. You can find nice words for things, and they sound fancy and pleasing. But then when you try to make things work in practice at a detailed level, then beauty quickly isn't preserved as nicely. Okay? So let me just give you, this is the basic scheme that one always has in mind. So string theory, of course, is most naturally defined in 10 dimensions. Okay? So the goal is, or the task is to start with an action in 10 dimensions where you can specify very concretely discrete input data. Okay? So you can define a topology of the space, a geometry, discrete sets of fluxes that are quantized in the standard Dirac way. You can have a discrete number of local sources and so on that are distributed in the space in a particular way. And so then the complicated and challenging task is to take this input and reduce from that input a low-energy, four-dimensional effective theory that looks like this. And so this low-energy effective theory will have a set of fields, like my phi field, but it might have more than one, and some of these might be time-dependent, some of them might be frozen. So you want to ask whether any of these light fields that you then are left with in this 4D effective theory, whether they can be suitable to drive inflation. So that's the basic scheme and philosophy of this business. So let me go through the different types of energy scales that you have when you do this dimension reduction from 10 dimensions to 4 dimensions. So the first energy scale is the one I mentioned before already. So we have the Hubble scale that determines when fluctuations during inflation are inside or outside of the horizon. So if I'm plotting energy scale on the vertical axis here, then high frequency modes are deep inside of the horizon, so sub-horizon modes, while low frequency modes are super-horizon. And this threshold value of physical frequencies of order the Hubble scale is what we usually associate with the energy scale of our experiment. Okay? That's the energy scale at which we're colliding inflaton particles, if you so wish. So if you think of inflation as a collision experiment, we're colliding these inflaton particles at an energy scale of order the Hubble scale. Okay, so then in string theory, of course, we have more fundamental scales at higher energy. So one scale is the string scale, which is set in units of alpha prime. So at frequencies below this string scale, we can describe things in supergravity, while at frequencies higher than that scale, we need full string theory to describe the dynamics. Okay? And that's why we usually choose this string scale to be above the Hubble scale. Okay? So that's not an absolute requirement. It could well be that inflation happens at a scale that is higher than the string scale. However, then in order to analyze inflation, you would need full string scatterings and so on. You couldn't just do a supergravity approximation to this. But I want to emphasize that this is just an assumption that we make to have a lamppost that we can study where we have tools that we can apply. Okay? It's not an absolute necessity, and it would be interesting to have more access to theories that are colliding inflaton particles at string scale energies, and because then your guesses might be that you will see more imprints of this heavy physics if you're closer to the threshold value. Okay, another scale, of course, in a compactification is the Kaluza-Klein scale, which we typically choose to be smaller than the string scale because we choose volumes that are large in string units, so that we have a geometric description of this space. Then we have the Planck scale, and we choose all the scales to be smaller than the Planck scale because this divides perturbative and non-perturbative quantum gravity. And then finally, we have the scale at which supersymmetry is explicitly broken. So this is not the breaking that's induced by the positive value of the energy density during inflation, but it's the breaking that even after the inflaton decays to zero energy density, supersymmetry might be naively restored, and you then have to break it a second time explicitly to explain why we don't see supersymmetry in nature. Okay? Again, this scale, M SUSY, could be living above the Hubble scale, which would then mean that it's irrelevant for describing inflation. Supersymmetry is already broken when we do this collision experiment of inflaton particles. Sorry?
MKK is the mass of Kaluza-Klein.
Yes. Which is determined by the ratio of the string scale and the volume of the compactification. Okay, I showed you the formula earlier. Okay. So all models of string inflation that kind of are claimed to be in control work with this hierarchy of scales, I think. Okay. So because then you have kind of supersymmetry helps you to stabilize your compactification to some degree because it's only spontaneously broken, and so you can still use it to compute certain things. with more confidence. And the string scale, we don't have to have, we can use supergravity as an approximation because the string scale is high. Oh yeah, and the Kaluza-Klein scale, if it had been below the Hubble scale, it would mean that we're scattering these particles really in a higher dimensional space. That inflation was a higher dimensional phenomenon, and that the universe only really effectively became lower dimensional after inflation. So people are trying to do this, I think. The problem I see with this, just at a first step, is that the scale invariance that we get for the fluctuations is really a consequence of 3 dimensions of space. Yeah? So scale invariance for the power spectrum means that the power spectrum, not the dimensionless one, but the other one, goes as 1 over k cubed. And the 1 over k cubed, this 1 over k cubed factor is coming from 3 dimensions of space. Scale invariance in 4 dimensions will be 1 over k to the 4th, or something like this. So if you really were producing these quantum fluctuations in a higher dimensional space, and then the space only became lower dimensional afterwards, you would have to explain how I go from a 1 over k to the 4th or 5 or whatever spectrum to something that is scale invariant afterwards. Okay? Which might be possible, but it's the scale invariance of the fluctuations smells 4-dimensional to me at least. Okay? Okay, so then just let me go through the basic ingredients that you might have. Some of them might be the inflaton field, and some of them might be nuisances that you'd have to control while you're inflating. So we call these moduli. They're zero energy deformations of the compact space. So there are certain scalar degrees of freedom that when I adjust them, when they change their VEV, they can do this at 0 energy cost. And so those would simply be massless fields in the 4D effective theory. And so examples for these type of at classical level, and then often these massless fields get potentials and masses from quantum corrections. So for example, one thing you can prove is that the vacuum Einstein equations are scale invariant. And so the overall volume, in fact, is a modulus if you just study classical Einstein gravity in those theories. And I want to show you this actually next time. The dilaton itself is a modulus. It's even a modulus in the 10-dimensional theory. Then we have 2 types of metric moduli. So the additional cycles and complex structure deformations of the compactification that can be light at low energies. We might have brane moduli by inserting localized sources of stress energy into the compactification, and the motion of these localized stress energy sources will appear as scalar fields in 4 dimension. And then some very attractive candidates are axions because they're protected by basically a high-dimensional gauge symmetry from getting large couplings to the UV degrees of freedom. Okay, so these are the kind of things that you could try. People have tried all of the things except maybe complex structure moduli haven't been tried as much. Because actually typically these complex structure moduli are stabilized, they get lifted even by classical effects, not just by quantum effects. So maybe that, in my definition of moduli, which are things that have 0 energy or 0 potential, at the classical level, they wouldn't even be moduli in that sense. Okay? So then, after you reduce the theory and you identify all these fields and compute their interactions and potentials, you might have a different, special types of spectrum of states for these fields. When we do single field inflation, we're basically assuming this. Yeah? There's a single light degree of freedom with a mass that is smaller than the Hubble scale, and everything else is decoupled from that to very high energies. So there might be things that live at the Kaluza-Klein scale, the string scale, and Planck scale, and so on, but none of these other fields will have been dropped down to the value of the inflaton mass. Multi-field inflation will be the situation where that's not the case, and you have several of these light fields. But then, especially in theories with spontaneously broken supersymmetry, I think it's quite natural, in fact, to have a spectrum of states with masses that live around the Hubble scale. Okay? So this would be anything that's stabilized and light in the absence of SUSY breaking, and then SUSY breaking might lead to a mass splitting of order the Hubble scale, like I was explaining earlier. So just because we have the ether problem, we naturally expect that there would be fields living at this threshold value. And in fact, we have a problem usually explaining why not all the fields living up here. Okay? So this is another, but this kind of spectrum of states, I think, is natural in a supersymmetric setting, but it's a bit harder to analyze what the fluctuations look like in this case, because these fields can still contribute to the fluctuations quantum mechanically during inflation. Okay? So, of course, you can see the challenge. So to derive this kind of spectrum of states and the interactions, we need to study in detail how to compactify the space, what the light degrees of freedom and their interactions are after you do this. Okay, and so this will take us an hour next time. Let me just quickly mention some of the common challenges that you find, and then I'll stop. So first of all, the first thing you realize, and this is something people didn't appreciate in the early history of these studies, is that you cannot decouple the inflationary dynamics from the stabilization of the moduli. Okay? So it used to be a hope that you can treat them separately, and so you can study some inflaton sector and you can worry about the stabilization of the moduli later. And it turns out that's not the case. And it's not the case roughly for the reasons that the inflaton field is UV sensitive and it doesn't decouple from very high scale modes. So you need a shifting of the moduli, for example, will affect the dynamics of the inflaton field, even if the moduli are relatively heavy. So it's hard to keep the inflaton light or to keep the dynamics decoupled from the UV physics. Another problem is that it's hard to arrange that there's just one light field. You know, if you have a mechanism that creates one light field, it often affects other fields as well and will make them light as well. But it's much harder to analyze the phenomenology of quantum fluctuations in many interacting degrees of freedom. And then finally, in order to compute this effective action, you never do this exactly. Okay? I mean, that's, you know, string theorists, they choose other corners of physical systems where they can do exact computations and, you know, ADS and whatever. Yeah? Here we just unfortunately don't have that luxury. Okay, so I cannot put myself into a box that's you know, I'm in the sitter. Supersymmetry is broken. The thing is dynamical and time dependent, so I can't study a static ADS situation if I want to describe inflation. Okay, just natural. But this also means that there's a set of approximations. And so a subset of these are always used when people calculating these effective potentials. And sometimes these approximations are well-defined, and more often they're not well-defined. And it's in fact rare that all of these approximations are well-controlled at once. So actually in our review, it's my favorite section of the book, or review in fact, where we have a chapter where we go through these different approximations and describe what is done. And you can take that list and map it when you see when you see a paper. You can look at their approximations, you can ask yourself, you know, was that a well-defined approximation or was it borderline, okay? At best, sometimes these things are borderline. At worst, they're just not consistent. Anyway, if anybody wants to hear anything about these, I'm happy to talk about it. But let me stop here.
Yes. Larger charge approximation,
What it is? Oh, it's basically large n. For example, when you put n branes in a space and back react them, you get ADS5. That's what it is. That's one of the better ones. I mean, so it's the opposite of that, because often what's done is the probe approximation. Probe approximation means you have the space and you put a single brane, for example, and you're imagining that the single brane is just moving probing the geometry of that space. But actually, what you find, and I'm going to describe next time, is that this during inflation, that brane isn't really a probe. It carries a lot of stress energy. That stress energy really feeds into the Einstein equation, and it perturbs the background space and the fluxes and everything. And that then feeds back into the dynamics of the brane itself, and so the whole thing has to be done self-consistently. And the eta problem term, for example, arises from the fact that the probe, once you add the brane, it changes slightly the volume in a way that depends on the position of the brane. And that's what's leading to the eta problem and things like that. So there's certain things that you don't see just by assumption. People have studied this in a probe brane approximation, and so you don't see that correction because you haven't allowed that brane to back react on the geometry. So things like that.
Okay, well, I'm afraid we have to.
Yeah, okay, sorry.